Respected Dr. Sameer Kamath, Dr. Joshi, dear friends, colleagues, and INAE members and people who are participating, good evening to all of you. This is the INAE Hyderabad chapter. Earlier we have AI and its application in defense application. Now this is the second series we are having materials for defense. I think nobody is better than speak on materials where challenges and opportunities are there, other than the Dr. Sameer V Kamath, DG Materials and Naval Systems. And everybody is aware of that one. Materials is very important component of any weapon system design. Based on that, what are the material is requirement? Material is available based on only designs are done. Now we are entering in the hypersonic regime, and where material requirement are totally different. For future of this future of material requirements and all, and what are the advances are going to happen, I think Dr. Samir is going to highlight some of challenges, what are there, and what are the opportunities we are going to get with that. With that, I'll request Dr. Joshi to give the brief biodata about the speaker. And after that...
Sir, we are unable to hear you. Good evening, everybody. It is indeed my very proud privilege to introduce Dr. Sameer V Kamath, who is currently the Director General of Naval Systems and Materials in DRDO. And he is Vice President of Indian Institute of Metals. Dr. Kamath completed his BTech Honours in Metallurgical Engineering from IIT Kharagpur in the year 1985 and PhD in Material Science and Engineering from the Ohio State University, USA in 1988. Dr. Kamath has provided leadership and direction to several critical materials programs in DRDO, such as development of high-strength steels for naval ship hulls, development of high-temperature titanium alloys and nickel-based superalloy based components for aero engines, development of tungsten heavy alloys for kinetic energy penetrators, development of fused silica radomes for missile seekers, development of armor solutions for personal as well as combat vehicles, and stealth materials for airborne and naval application. These have found use in various systems being developed for DRDO laboratories. Dr. Kamath is a fellow of Indian National Academy of Engineers and Institute of Engineers. He is recipient of various awards. I want to name only a few of them. He is a recipient of Distinguished Alumni Award from IIT Kharagpur, Metallurgist of the Year Award from Ministry of Steel, Scientist of the Year Award from DRDO, and Silver Medal. He is currently the Vice President of Indian Institute of Metals and member of Governing Council of INAE. Over to Dr. Kamath to enlighten us with your talk.
Thank you, Dr. Joshi, and thank you, Shri Yadav, both for the kind introduction. So let me share my presentation first. I hope you are able to see my presentation.
Yes, we are able to see.
So, good evening, everyone. I would like to thank INAE Hyderabad chapter for inviting me. I would have liked to be there personally to deliver this talk, but where the pandemic situation has again flared up, I think online was the only way we could go ahead with this talk. So today, I'll talk about materials for defense systems, challenges and opportunities. When Dr. Joshi asked me to give this talk, I gave this title without really thinking about what I would talk about in this talk. When I actually started making my slides, I realized that materials are a very diverse field. And for me to make a coherent talk on such a topic would require at least 3 to 4 hours. And I am sure that none of you have the patience to hear me out for 3 to 4 hours. So what I did, though I didn't change the title, what I will focus on today in my talk is the challenges on opportunities in structural materials, especially metallic alloys. So with this brief introduction, let me move to my first slide. So materials technology underpins almost all defense systems and is a key enabler for significant improvements in performance of defense systems. For example, if you want a submarine which can dive to a higher depths or greater depths, you need to develop a steel with much higher strengths without losing its ability to be welded, without losing its toughness or corrosion resistance. This provides a very tough challenge for the material. As Sri Yadav mentioned, if you want to have your missiles move at hypersonic speed, you will have to develop materials for the nose cone and leading edges which can withstand that temperature. You will also have to develop a material for the combustor which can withstand the very high temperatures in the scramjet engine. If you want to develop a higher penetrating kinetic energy penetrator, you have to find a material with very high density, but which has sufficient strength and toughness to withstand the very high stresses that it experiences within the gun barrel. So as you can see, if you want a significant improvement in the performance of your defense system, you have to be able to develop newer materials with better properties. Broadly, materials can be divided into structural materials and functional materials. Structural materials are materials which sustain the load and are used to make the structures of various defense platforms or defense equipment. Functional materials, which I have listed out here, perform a specific function. For example, magnetic materials can be used to provide a magnetic field or provide a flux. A shape memory alloy can be used to provide actuation. A radar absorbing material can be developed to provide stealth in a particular EM band. But as I discussed in the beginning, for today's talk, I will focus on structural materials and especially metallic materials. This is because although the usage of composites is increasing rapidly, especially in aerospace, metallic alloys are by far the most predominant materials used in structures for defense systems. So let me first start by talking about some broad challenges which materials development face, especially structural materials. The first major challenge is the requirement for these materials are very low, and that too they are sporadic. That means you don't get regular requirement of such materials. Just to give you an example, India's steel capacity is about 130 million tons of steel per year. If you combine all the requirements of steel for defense applications today in the country, it barely touches 10 to 12,000 tons per year. Now you can imagine the country's capacity is 130 million ton and your requirement for defense applications is of the order of 10 to 12,000 ton. It's hardly a day or two's capacity. So it is really not that attractive for the industry to make such materials. That is the first challenge that we face. This is more so in the case of steels and less so in the case of special materials which don't have that much civilian applications, such as titanium alloys and nickel-based superalloys. The other major challenge for making defense materials in large quantities is the stringent qualification and certification requirements. For most civilian applications, though quality is important, they don't require such stringent qualification and certification. This makes the industries very reluctant to take up defense materials. Not only the volume is less, but they have to put in a lot of effort to get themselves qualified and certified for production of such materials. Other limitation or problem that we face is that designers expect that every material in all product forms should be available indigenously, and that too at a cost which is lower than that available from global sources. A lot of time capability exists. By capability I mean both knowledge as well as infrastructure. But the material is not made because the volumes are too small, which makes it economically unviable. Sometimes there are no significant knowledge gaps, but there is lack of infrastructure for specific products. For example, let me give you, if you want to make 7000 series aluminum alloy plates, you need a stretching machine and you need a heat treatment furnace after stretching to do the aging. Currently, we don't have such facilities for thick plates of aluminum alloys in the country. So though the capability exists to make such plates in the country, they are not being made because of lack of infrastructure. Now, this kind of infrastructure would need an investment of about 800 to 1000 crores. But the current market size for aluminum alloys in terms of such high strength aluminum alloys does not justify investment of this order. So though the capability exists, it has not yet, this infrastructure has not yet been put in place in the industry in the country. And hence we are still dependent on imports on 7000 series plates. But the major challenge that we face is that the development time taken for materials, if you look, I have given a broad timeline, 5 to 15 years. 5 years is what is needed if you just want to indigenize a known material. And if you want to develop a totally new material, it takes anywhere from 10 to 15 years. As I will discuss later in my talk, this is becoming unviable and there is a great need to shorten this time period for development of new materials. But I will highlight this later in my talk. So let me go ahead now. So this typical development time for new materials is not based on what is the requirement within the country. If you look at anywhere, this slide I have taken from Robert Shafrick of GE Aircraft Engine. And if you see the time periods that he has mentioned, that really matches to what we have found is required within India also. So what he says is for a usage of an existing material for a non-critical application, you need basically 2 to 3 years. For usage of an existing material for a critical structural component as in defense or aerospace, you need up to 5 years because you have to go through the certification process. For any new material development for a system for which there is experience, it can take up to 10 years. And for any new material class which have not been used for any given application, you need anywhere between 15 to 20 years. Now you may ask, why does it take such a long time to do materials development? So if you look at this slide, the first phase, which is the material science phase, usually happens within 3 to 4 years. And this is where you see a lot of excitement and you see a lot of literature and you hear about a lot of new materials being discovered. This is where you basically work at TRL 0 to 1, 0 to 2 levels, and where you're focused on developing a material at a laboratory and you look at only a few properties of interest. You hear a lot of exciting things about a lot of new materials in this phase. But then once you try to move from this material science phase to the materials technology phase, where you have to look at scaling up the process, looking at its machining, looking at its joining, repair technologies, how to look at it, how to do non-destructive evaluation for various components, how to generate enough data that designers have confidence, how to go through the qualification process. This part can take anywhere between 5 to 10 years. And experience has shown, and this is experience globally, that 90 to 95% of all materials discovered in the first phase fail to go through to production because of some issues or the other with some of the properties mentioned here. So this is also called the valley of death. So only about 5 to 10% of the materials which you hear of in the material science phase usually translate to production. And eventually, once production happens, it takes some time for cost estimate, for the cost and optimization of the process, and to find different applications for such materials. So that is why this process takes a long time. So now, with the help of some case studies, I will highlight some of the challenges that one faces, which I broadly discussed in my earlier slide. So if you look at the materials development that has been undertaken in DRDO, and since I'm dealing today mostly with metallic alloys, most of this development has happened in DMRL Hyderabad. So I have taken, though I have listed out all the materials that have been indigenized and also new development which has happened within DMRL, I will take 4 case studies, that is naval steels for ship hulls, titanium sponge development, ultra high strength steel, that is DMR 1700 steel development, and nickel based superalloy development. So with the help of 4 case studies, I will try to bring out the challenges that one faces. So if you now look at steels for ship hulls, to meet performance and design requirements, the steels for such applications should possess sufficient yield strength, adequate ductility, excellent Charpy impact toughness at sub-zero temperatures, excellent weldability, and good corrosion resistance. Now, of the many classes of steels, high-strength low-alloy steels are ideal candidates. Now, in the middle 90s or late 90s, the Indian Navy wanted to start designing the first Indian aircraft carrier. So when they looked at what steel to use to make this aircraft carrier, they settled on a high-strength low-alloy steel. And if you see the comparison of the properties of various high-strength low-alloy steels which are available in literature, you can see that this ABA steel, which is a Russian steel, has the best properties. So Navy decided to go with the Russian steel, ABA. But at that point, I think it was just after the Pokhran explosion. So Russia was playing hardball in terms of giving the steel to the Navy to start construction of this, or to start even the design of this steel, or to start design of the ship. So Navy approached DMRL in the late 90s to see if such a steel can be indigenized within the country. And the only information which was available to the lab was the composition of the steel. So the composition of the steel is briefly given here. So it's a micro alloy, high strength, low alloy steel, that is ABA, which DMRL undertook the indigenization for. For people who are not metallurgists, it appears that once you know the composition, what is the big deal in making the steel? But let me tell you, composition, knowing the composition is only knowing about 5% of what is required to make a steel. Because the real challenge is to how to process the steel to get the desired microstructure, desired impurity contents in the steel to get the desired properties. So DMRL took up this challenge. They first made the steel within the laboratory at about 80 kg scale, which is the kind of furnace which is available within DMRL for steel making, and established that we could achieve the properties of the steel at lab scale. But you can imagine the next challenge is to scale up directly from 80 kg to about 80 tons, because the country does not have an intermediate capacity. So there is no intermediate capacity where you can try out making it at, say, 2 ton or 5 ton capacity. Directly from 80 kg, one has to scale up to 80 tons. Luckily, the Indian steel making industry is fairly mature, and we could find a very good partner in SAIL. And we could, using primary steel making plus ladle refining, and eventually settling on a continuous casting route, though we initially started with the ingot route, we could make this steel with a targeted microstructure which you could get from literature, that is a fine grade ferrite with uniform grain size, minimal inclusion content, and very little perlite which is not contiguous. So using the processing available at Rourkela, we could achieve such a microstructure. And the kind of processing which is required to make plates of such steels, you need to be able to do controlled rolling plus accelerated cooling. When we started this in SAIL in early 2000s, the rolling mill at SAIL did not have the capability to do this water cooling. And hence, initially we could make only thinner sheets. But by the time I think we reached 2005 or 2006, this water cooling facility was also installed at Rourkela Steel Plant in their plate mill. And we could achieve thicknesses up to 21 or 23 mm at RSP. Now, the facilities in the country have improved dramatically, and we have now roller quenching facility available with most of these high-end rolling mills. And today it is possible to even make 100 mm plates in the country, even for steels which require to be quenched to retain their martensite, which I am not going to talk about today. But the facilities within the country have dramatically improved in recent years, that today we are now in a position to make any thickness naval steel plate of any composition for warship construction. So, to summarize, in this, there was a user need, there was a mature industry available, although initially facilities were not available. With the help of laboratory studies at DMRL and the help of the expertise available for scaling up at SAIL, we could achieve making the steel in the desired thicknesses and desired widths for the aircraft carrier. As you know, if you want to make an aircraft carrier, you will need to make weld consumables which can be used to weld such steels. that activity was taken up by a sister laboratory, NMRL, and they have been able to develop all the required weld consumables with the help of Midhani and several MSMEs within the country. And today, I'm very happy to tell you that Indian Navy has taken a decision that henceforth all naval ships which are going to be built in the country will use this DMR 249A steel that was developed in the country by DMRL and SAIL. Today now, there are several other industries which are capable of making this steel plates. You have JSPL, you have SR, which is now ArcelorMittal Nippon Steel. So the cost of production, so just to tell you the kind of benefit that we get if we can indigenize a lot of the materials within the country, the cost of imported steel plates was the order of 300 to 400 rupees a kg. When we first indigenized it, the cost dropped to 150 rupees a kg. And today these steels are available at 70 to 80 rupees a kg. And in a typical aircraft carrier or the aircraft carrier which India is building, you need 40,000 tons of steel. So you can imagine the kind of cost saving you can get if you are able to indigenize such a steel within the country. So I will say this is one of the major success stories for indigenization. And the drive provided by the user also played a key role in making this a success. So now let me move to the second case study. So if you look at India has a very long coastline, and all along the southern peninsular coastline, we have large reserves of ilmenite, which is a titanium containing mineral in the beach sands. Now, if you look at the titanium technology cycle from the beach sands, you have to basically mine the beach sands, then beneficiate it, separate out the ilmenite, and then do carbon chlorination to get titanium tetrachloride, then purify the titanium tetrachloride, and then using either sodium reduction, magnesium reduction, or fused salt electrolysis, make titanium sponge, and then use this titanium sponge and add different alloying elements to make the different titanium alloys which are required for aero engine program or the airframes. Now, if you look at in the 70s and 80s, KMML had already established the process for making TiCl4 from the beach sand minerals found in Kerala. So that this plant is located at Chavara in Kollam district of Kerala. Midhani, which was established in 70s, also had developed capability to make various titanium alloys in different mill products using imported titanium sponge. But what was missing was this technology required to convert TiCl4 to titanium sponge. So DMRL in the late 80s or middle 80s started a big effort to set up a pilot plant within DMRL to see if this technology gap could be bridged. So I will not go through the details here, but if you see, you basically need to first purify the titanium tetrachloride, which was obtained from KMML. Subsequently, this titanium tetrachloride was reacted with the magnesium in this reactor to form titanium sponge plus 2 magnesium chloride, which was then recycled to get magnesium from the magnesium chloride, which can then be used again to reduce titanium tetrachloride. So this combined process was established within DMRL. after a long effort of about 10 to 15 years. And I think the credit for this goes to Shri R.V. Subramaniam and his team, which started from really scratch and established the entire pilot plant and ran it within DMRL for 3 to 5 years. So this is the first 3000 kg titanium sponge cake, which was obtained from DMRL pilot plant. So as you can see the date here, this was established in 2003. So although the technology was established in 2003, there were no takers to set up a full-fledged commercial plant. So from 2003 to 2007, we had a great technology, but no takers to set up a plant. In 2006 end or 2007, luckily ISRO decided, because they were finding it tough to obtain titanium sponge from the commercial market, because at that point there was a sudden demand for aerospace applications for titanium sponge. Hence, the availability of titanium sponge in the global market had become a challenge. So ISRO decided that they will fund this plant. So though the technology was established in DRDO, it was ISRO which funded, and the logical choice to set up this plant was KMML, because they already were producing titanium tetrachloride, which was being converted to titanium dioxide for various other applications, industrial applications. So with DMRL technology, ISRO funding, and KMML as the nodal agency to set up this plant, the project started to build this plant in 2007 or 8. And by 2011, this plant was commissioned. There were a lot of teething problems initially, but by 2014-15, the commercial production from this plant started. But one of the issues which happened is, because of the limitation of funding, only a 500 ton per annum plant was established. Now, if you see globally, most global plants operate at 10,000 tons per annum. Now, you can imagine that when you operate at 500 tons per annum, when others are operating at 10,000 tons per annum, you have no economies of scale. And the cost of production of titanium sponge is definitely going to be higher than what you get from global sources. So KMML struggled to sell their titanium sponge to industries within the country, other than that mandated by VSSC or our strategic program. So here is an example that you have established a technology, but unless you are willing to scale up to a capacity which can compete with global players, it is very difficult for the technology to survive in the long run. But I am glad to tell you that now there is an effort in the country to see if this plant can be scaled up to 1,000 tons and eventually to 5,000 tons per annum. Now, a 5,000 ton per annum requires an investment of about 5,000 crores. So it will need, I don't think government alone can fund such an expansion. So it would need some industry to put in their money. But again, competing only by supplying to Indian industry is not going to make this plant viable. You will have to become a global player, and hence you will need a large enough industry which can compete globally to sell the titanium sponge produced from such an industry. So here's an example of a good technology established after a lot of effort, but so far it has not borne the fruits which was envisioned. Unlike the first case, naval steel, which has been continuously used or being continuously used because of a regular requirement from the Navy. So now this is the 500 ton per year titanium sponge plant. The plant is still running, but now it is nearing 10 years and it either needs to upgrade its reactors or to scale up production to survive in the long run. Now let me move to the third case study. This is DMR 1700 ultra high strength steels for rocket motor casings. Now again in the late 80s, early 90s, Maraging steel was the steel of choice for making rocket motor casing boosters because of its attractive properties of a good combination of strength and toughness, and also the ability to work with the steel in low strength condition and then subsequently heat treat it to get the high strength without really going to very high temperatures. You can age Maraging steel at 400, 450 degrees centigrade to achieve the high strengths. So in DMRL, in the late 80s, there was a thinking. One of the limitations of Maraging steel is the cost, because it has more than 30% alloying additions and expensive alloying additions like nickel, cobalt. So there was a thinking in DMRL that whether can we make a low alloy steel, and when I mean by low alloy, I mean alloy content less than 8%. Is it possible to design a low alloy steel which has comparable properties to Maraging steel, and where you can do quenching by air cooling? So it has sufficient hardenability that you can get martensite just by air cooling, not by quenching in water or oil. This will avoid distortion. So this was the broad thinking in DMRL, and this was when Dr. Ramarao was the director, and Dr. Ramarao and Dr. Malkonde took up this activity in the late 80s, early 90s. So the Maraging steel, the 250 grade Maraging steel, is the Maraging steel of choice for such rocket motor casings. And so our target in DMRL was whether we could develop such a steel to have comparable properties to the 250 grade Maraging steel. So basically R&D right from basic studies was started at DMRL, where we looked at the effect of alloying elements on strength and fracture toughness of iron as well as nickel silicon chrome steel, which is a base steel which had good properties in literature. So this was a PhD topic of Dr. Srinivas, who was then scientist in DMRL. He has retired now, of course. So in his PhD, he looked at this basic study on seeing how different alloying elements affect strength and fracture toughness of pure iron as well as some basic nickel silicon chrome steel. He found that cobalt significantly enhanced the fracture toughness, but it reduced strength. Whereas molybdenum increased strength without compromising too much on fracture toughness. So he then tried various lab scale melts to optimize the cobalt and molybdenum content in the steel, that is the nickel silicon chrome steel. And after a series of experiments, he was able to identify a suitable composition which more or less met the requirements of the properties of maraging steel. This was then scaled up using vacuum induction melting and vacuum arc refining at Midhani. And a process for forgings, plates and sheets was established in Midhani. So DMRL was not the only laboratory in the world which was looking at trying to replace maraging steel. VSSC in the country, and there were several other universities and industries within the world which were also trying to replace maraging steel. But you can see here that the steel developed at DMRL had the best properties among the various types of steels, low alloy steels being developed anywhere in the world. Now this steel, DMRL even went ahead and with the help of DRDO made one booster motor casing for Akash. And it was proof tested and it met the requirements of the casing, whatever designers' requirements were there in terms of yield pressure as well as burst pressure. But at that point, DRDO, which was driving this application, felt that the benefit of using such a steel, because you see, if you look at the cost of the material in a missile is hardly 10% or 15% of the overall missile cost. And they did not want to replace maraging steel because by then maraging steel was being made within the country and it was easily available from Midhani. So this program didn't go ahead. It remained at this stage. But DMRL explored whether this steel could be used for other applications. And since DMRL was also looking at armor applications for our Arjun Mark 1A program, DMRL was able to use this steel and much higher plate thicknesses, of course, 50 mm and 80 mm, which was made at SR Steel. And DMRL was able to use the same steel for armor application. And it has helped in reducing the weight of the Arjun armor by about 10% and will now go into the Arjun Mark 1A, which has been ordered by the Army recently. I'm also happy to tell you that recently, due to the efforts of MSR Prasad, ex-DG MSS, and DMRL team led by Director Madhusudan Reddy and DRDL team led by Shri Yadav and Dr. Joshi, a flow forming route for this steel is being established. And there is a possibility that for future tactical missiles, this steel could also get used. So you can see that though this was a new material which met the requirements of the target properties, it eventually got used for a different application. So these are some of the lessons which one can learn, that although you may develop a material for a given application, you should also explore what other applications it can work for. So now let me go to the final case study, that is materials for aero gas turbines. So I will look at nickel-based superalloys. Now nickel-based superalloys are used in the turbine section of the Kaveri engine, which was being developed by GTRE. And if you look at by weight, nickel-based alloys comprise 50% of the weight of the aero engine. Now, the turbine blade, which is a very important component to improve the efficiency of the engine, if it operates at a higher temperature, you can get higher efficiency for the engine. So DMRL, using imported alloys, has been able to develop various components or equiax blades, directionally solidified blades, or single crystal blades, equiax, directionally solidified, or single crystal blades, using imported alloys, as well as some of the alloys were also indigenized at Midhani, like CM247LC. But DMRL also took up development of most of the, one thing I forgot to mention is most of the alloys were either first generation alloys or second generation alloys. In the late 90s, early 2000, DMRL also thought that for future requirement, we should also develop third generation nickel-based super alloys. Third generation alloys are alloys where you have rhenium additions of about 6 to 7%, which gives much higher temperature capability. So DMRL took up development of both a single crystal alloy and a directionally solidified alloy. And DMRL was successful in developing these alloys at lab scale. Now, if you look at the temperature capability, the DMRL developed alloys, that is the directionally solidified alloy as well as the single crystal alloy, have very good properties with respect to what is available globally. And if you look at its mechanical properties, they are also very good if you look at imported materials, both in terms of stress rupture as well as in terms of 1% creep strength. But the alloys have remained at lab scale. There are two reasons for it. To scale up, such alloys are very expensive. The cost can go up to 2 lakhs per kg. So unless there is a clear-cut application in mind, scaling this up and proving it at an industrial scale is prohibitively expensive. And the engine program also did not go forward. Again, now there is talk of a 110 kilonewton engine. But here again, the 110 kilonewton engine is going to be developed with a foreign OEM as a partner. So I am not sure whether these alloys will even be considered by that foreign OEM partner, because each engine OEM have their own alloys. So here is a situation where using a lot of R&D efforts within the lab and alloys were developed, but it is very unlikely that it is ever going to get used. So this is a lesson also that one has to be very clear when we take up new alloy development, how eventually we plan to get it used in a given application. So now let me come to the main challenge, which I think is also an opportunity for the future. How one can reduce new material development time from 10 to 20 years at present to about 5 to 7 years. So if you now look at the defense system development cycle, the design team usually takes the materials data from a database of materials, designs its system, and then passes it on to manufacturing systems and the integration team. The current system design and development cycle outpaces the materials development cycle. This is of the current design and development cycle for most defense systems is now of the order of 5 to 7 years. So unless the materials development cycle shrinks to meet these timelines, insertion of new materials technologies is going to become much more difficult and less frequent. And that is the rate limiting factor for design. So we have to be able to replace this database of materials with a materials team which can develop what is the requirement of the design team, a material which is required by the design team within the time frame of the designer's development cycle. So this is designated here. And to do this, we have to find ways to design materials similar to how architects design buildings, or how electronics engineers design circuits, or how civil engineers design bridges. But it is not as easy as it is in other engineering disciplines, because there are several critical missing links. The predictive computational materials engineering models to correlate from either the atomic scale or the microstructure scale to the final properties which the material will get or will possess are not available because of the complexity of the various phenomena and the variety of materials which one can make. There is also a missing framework which is required for seamless transition of models across length and time scales. So unless these missing links are taken care of, this approach is very difficult to implement. Luckily, I think globally the materials community has woken up to this challenge, and a systems level approach to materials design, optimization and implementation has been taken up very seriously over the last 10-15 years. The two major initiatives towards this are known as Integrated Computational Materials Engineering, that is ICME, and the Materials Genome Initiative. Both these initiatives have started off in the US, but now have percolated to different countries. Whereas ICME, the focus is mainly using computational tools. Materials Genome Initiative is much broader based. It not only looks at computational tools, but it also looks at experimental tools for doing accelerated experiments, and also digital data using artificial intelligence and machine learning, and using the vast data which is already available to see if one can quickly develop newer materials using the lessons learned from previous materials development. So basically, if one can develop this ICME and Materials Genome Initiative techniques, one will be able to change this linear materials development continuum to a circular materials development continuum, where instead of sequential approach, where one goes from discovery to development to property optimization to system design to certification to manufacturing, at any given stage, there will be interaction and parallel efforts going on in all fields or all disciplines, which will be able to shrink the development cycle from 15 years to about 5 to 7 years, or at least that is the hope. But there are several challenges in implementation of ICME or material MGI, that is the Materials Genome Initiative. Basically, you will need a culture shift in the way materials research, development and deployment are done. It will need integration of experiments, computation and theory, which rarely happens in the present condition. It will need access to digital data. A lot of data is available, but because of IPR and other secrecy related issues, the data is available only to limited sets of people. There is no widespread access of data, and unless a proper framework and proper system is established, this access to digital data is going to remain limited. You will also need a well-equipped workforce which can meet or work in the different style to what is being done today. So let me just briefly elaborate on each of these factors. So if you look at how collaboration happens today in materials field, collaboration usually is confined to narrow teams of scientists having similar expertise in theory, experimentation, or simulation. These collaborations will be much more fruitful if it is across all three domains and also with industry during the R&D process. The advances which happen during basic research should also be transitioned and integrated into engineering practice and application. If a multidisciplinary approach such as this is followed, then the culture change can happen, but it is easier said than done. If you also look at integration of experiments, computation, and theory, integration of tools, theories, models, and data from basic scientific research rarely happens with people who do processing, manufacture, and deployment of materials. The first three things remain within academia or some R&D labs and rarely get translated to industry where processing, manufacture, and deployment happens. You would also need to create a materials innovation infrastructure that will enable this integration by providing access to digital resources that contain property of known materials as well as the computational and experimental tools to predict these characteristics for new and emerging materials. So challenge is to create an integrated network for material resources. Again, as I briefly mentioned, access to digital data is going to be crucial. And with the limitation of data security, IP, how we can implement best practices for sharing materials data is going to be critical if one has to access digital data in the future. A well-equipped workforce must be trained in such new research methods. So this will require basically our universities to change their curriculum. Much more synthesis or much more simulation and modeling has to be taught within our curriculum in the materials field. And also there will be need to improve interactions or between modelers and theorists and people who actually make and characterize and implement materials. So this new curriculum development and implementation has to be started at the earliest if we have to meet the challenges of MGI, ICME in the future and meet the opportunity to get new materials implemented in new designs within the time frame of 5 to 7 years, which is required now with the shrinking of the development cycle. So DMRL has taken up a ICME type project to see if we can develop a powder metallurgy nickel-based superalloy aero engine discs. All the tasks that have been indicated here are being addressed through modeling, together with identifying the gaps and bridging interfaces to be worked out for progressing towards accelerated development of this powder metallurgy disc using a new alloy which is equivalent to the N18 alloy which the French are using to make such discs. So I hope with this exercise, DMRL will be able to establish at least a framework for accelerated materials development for the future. Here I would also like to add that INAE also has taken an initiative to see how the resources available in the country can be synergized to push this ICME MGI type approach for accelerated materials development in the country. And this report for this should be submitted to INAE within the next 2-3 months. And I hope that that will give an impetus to such accelerated materials development efforts within the country. So with this, let me summarize today's talk. Materials are a core technology for defense systems and key enablers for advances in defense systems. The current capabilities for developing and manufacturing any metallic alloy in the country required for structural applications for defense is quite good. And with the maturity of academia, R&D labs such as DMRL and industry in the country, I think we can undertake the development of any material required within the country. However, a paradigm shift in the way R&D in materials is currently being done will be essential to meet the future challenges. And this is also the biggest opportunity. So with this, let me thank all of you for your kind attention. Thank you.
Thank you very much, Dr. Kamat Sahab. If any of the participants have any queries or questions, we are ready to take.
People can ask the question if somebody is having some doubts.
Yeah, this is Rear Admiral Srinivas, ADG Acquisition Technical MOD.
Good evening, Admiral Srinivas.
Very good evening. I just have one small query.
Yes.
This development timelines of 10 to 15 years is of course essential. Possibly for the cases where a particular material is presently not existing or it is not developed anywhere. Possibly the material is available elsewhere in the world.
Then it takes about 5 years. Then it takes about 5 years.
Some kind of a takeoff level for this. Say for example, in case we are looking at the material science level technologies, in case if we are pursuing, and in case if you are aiming at a particular material of a particular composition, possibly that will be available elsewhere in the world. And even the technology related ones, I meant to say that this manufacturing process ones, we can possibly take that material and then continue to do with that. And then subsequently just a verification kind of a thing when our material, our own developed material from the material science level, when it actually matures to technology level, we need to quickly possibly validate and for this manufacturing process in a very short time. So possibly in the areas where the material is already available elsewhere, like in the case of DMR249 and other things, the Russians already have it. We plan to develop it in the country. So since it is not an ab initio development of material, we may look at concurrently taking up various stages of development to reduce the timelines from 10 to 15 years to slightly a shorter timelines. You did touch upon that during at the end of it in the approach. So possibly we may we may not take it at the first kind of a thing that every material would require 10 to 15 years of development cycle.
No, I also mentioned in my talk, our experience has been for indigenization, we need about 5 years. For new materials development, we are taking about 15 years. For any indigenization, now the maturity for metallic alloys within the country is very good because we have good maturity now within academia, R&D labs and industry. Other than if you look at niobium alloys or very specific metallic alloys where there is no experience, in most metallic materials, in aluminum alloys, titanium alloys, steels, we have enough expertise now in the country, we will be able to indigenize any of them within 5 years.
Absolutely. Actually, taking a little cue from that, like actually I've done a few case studies on aluminum magnesium alloys. You find that a lot of materials which are being imported right now, either it is being made either by like Balco or somebody, or like even if it is so like it just only amounts to developing a clone of one thing which is already available, and then again quickly validating it for the purpose for which we are like looking for a material. But if you look at most of these platform manufacturers and equipment manufacturers, including our DPSUs, we have actually been importing it. In some cases, what is happening is the way the TOTs have come for the platform from different origins of countries. If he uses a particular his own standard, we are buying it to his standard. And the similar material on a different platform, in case of a different origin, we are buying it for a different standard because he told us that the material is of this standard. Possibly, if we just do in the complete materials range, I meant to say that like 1000 series and 2000 series and all the series. If we do mapping of various applications, both in defense as well as outside, and then if you make a bubble, diagram kind of a thing, the amount of annual, requirements, and then the different applications. If we plot all these things, Dr. Balamurali was talking about the knowledge, diagrams in relation with some other work that we were all doing. If we actually have these things plotted, wherever we have very highly dense, the mapping of these materials that we are using, possibly we may develop our own, family of materials in that particular area, and then tell everybody to actually migrate to this material. So having our own material, conforming to either IS or any other standard, in the whole, range of materials is actually, I feel, is the need of the hour, possibly to consolidate the requirement. Otherwise, the same material to different standards that different people, we are actually either importing or we are trying to manufacture.
I fully agree with you. We have to do this mapping and identify where the volumes are sufficiently high for the industry to take up. The challenge is it is not possible to make every material in every product form within the country because you don't have economies of scale. So the cost is then going to become higher than what you get from imported stuff. So one has to really identify which materials are required in what quantities in what product form and invest those infrastructure which is required to make that material within the country so that we have good economies of scale and we can compete with global sources. Because you see, unless it is forced, companies prefer to save money. So they would rather import. If you can make a material with a higher cost, it is not sustainable in the long run.
That's right.
So we have to worry about cost if we have to sustain that industry. And our industry also, materials industry, has to not only look at defense applications within the country. Our market is not large enough for defenses. We have to look at exports, not only of the defense system, but also of the materials. So we need large enough industries which can do marketing of these materials outside the country and get into the supply chain of global defense manufacturers.
That's right.
Thank you.
Thank you very much.
Any other question?
Anybody has got any questions? Dr. Kamat will be very happy to answer.
Either I was very clear or nobody understood, sir.
It is very good talk.
Very clear.
It's
Very clear and then very lucidly
informative.
presented.
Dr. Joshi, then I think we should try to conclude this.
Yes, sir. Yes, sir.
Uh,
Thank
I
you
think,
very much.
only thing, sir, I want to thank Dr. Sameer Kamath. With his busy schedule, he has agreed, and I think this is a one-of-kind of talk where I think maximum people might have got benefited. At least people understand, because first time I am personally finding the material can be developed based on the requirement. Generally, as a designer, what we do, what all material is there, we get property, try to design out of that. If this, what I'm telling, if this liberty is given to designer, particularly DRDO and all, our miniaturization and so many systems, so we can do wonders. But his timeline is looking very big. I don't know how to reduce those things.
Yeah, that is the challenge, Yadav sir, but that is the future also. That is the challenge, but that is the future.
Nobody will wait for 15 years. That is my problem. By the time
Correct. It has to be shrunk. It is a challenge of the materials community to develop materials much faster than what they have been doing.
this concept is really good, as he's rightly saying, maybe new technology, new computers, new computing system, new AI and all, try to bring down this time. And certainly defense industry will be the first thing to get benefited out of that. Thank you very much, Dr. Sameer Kamath. I think excellent lecture talk. A lot of people might have got benefited. Now I'll tell Dr. Joshi to try to conclude with this. Okay.
Thank you very much, sir. All the participants. Very good questions asked by Admiral Srinivas Sab. Admiral Srinivas Sab, in fact, we have to, at the highest level, we have to take up the activity of pushing our indigenous product in all our systems, whether it is naval system, air force system, or any of the systems, so that it gives a thrust to our local industry. I hope all the designers of the missiles or ships or aircrafts will take this point, keep this point in mind. Thank you very much, Kamat Saab, for sharing your knowledge and giving us idea and the overall perspective of how the materials, what are the technologies you have developed, and how the material development cycle is being shrunk now. So hope that we'll shrink the material development cycle so that we can develop in our missile or shipbuilding activities. Thank you one and all, and thank you, Kamat Saab. I profusely thank INAE for giving this opportunity to host this event. Thank you.
Thank you, everyone. Thank you.